Thank you all for joining us today. It is my pleasure to introduce Carey Witkov from MIT's Department of Physics, presenting on differential equation parameter estimation and model testing via simplified chi-squared minimization.
Uh, Thank you, Kevin. Yes, I'd like to talk to you a little bit about this model testing method. And by way of introduction, and let's see here. There we go. Uh, just by way of a little bit of a background, this method of parameter estimation model testing is widely used by particle physicists and astrophysicists, and they've had some pretty impressive applications, including discovery of the Higgs boson, gravitational waves. I first learned the method by having to teach it, and worked with Keith Zengel, who was a particle physicist before we taught together, and he worked at CERN at the Atlas project at the LHC to find the Higgs. And we ended up simplifying the method that was being used. So we were teaching it in the Harvard physics lab for introductory physics. And we wrote a little book. It was published by Oxford University Press in 2019. The Python code's available at GitHub to implement chi-squared analysis, as we'll be talking about presently. And the method's simplified enough that not only taught to undergrads, but succeed in teaching it to motivated high school students in research projects. So this talk, it will introduce chi-square analysis via algebraic models that are derived from ODE models, and we'll see why that is advantageous. There's actually two reasons for that. One is it simplifies the measurement data collection, and it also avoids numerical differentiation, which tends to magnify noise. The motivation, hopefully this could contribute to ODE model testing. This is my third Simiode. I want to thank Brian for making this wonderful conference available each year. And a couple of observations I've had, both from talks and reading books on modeling differential equations that are used as textbooks. And it seems like modeling is easy and model testing is hard. And get the impression that model testing is kind of the Wild West of ODE modeling. There's so many methods used, including the ever-present eyeball method that it looks like it's a good fit, and many others. But these model testing methods are often unrelated to the methods used to estimate parameters. So I'd like to emphasize that these two problems are inseparable: parameter estimation, getting the best fit parameters, and model testing. To make clear the terminology, so y equals ax, that's not a model. It's a family of models, one parameter linear models. Y equals 3.4x, that's a specific model. Now, to find the best fit parameters requires that we start with a family of models, but then testing the model requires the best fit parameters. It's circular, and both problems should be tackled together. In fact, both require measurement uncertainties. I mean, after all, how can you test a model if you don't know how uncertain your data is? And how can you be sure you have best fit parameters if we don't know the uncertainty in the data as well? This means we require multiple trials. And that sets it apart from what we often see in model testing, where you'll see a model developed, then some XY data with only one value for each data point. No, we have to use multiple trials, and that means mean values for the data points. So chi-squared analysis is one consistent methodology that applies for both parameter estimation and model testing. Here's a simple example to kind of complete this introduction, the motivation. A simple pendulum model. On the left side is torque equals moment of inertia times angular acceleration. a simple physical model for a simple pendulum. And then we work our way down small angle approximation to a differential equation. On the right side, what we've done is we've noted that this is the differential equation for a simple harmonic oscillator. So from working with simple harmonic oscillator equations, we know that the coefficient of the variable can be set equal to the angular frequency squared. So we extract from the ODE the equation on the top right, from which we now derive a one parameter linear model, y equals ax. And notice that this is an algebraic model. Length, which was a parameter in the differential equation model, is now a variable in the algebraic model. Well, what are some of the advantages of working with the algebraic model? One is you're dealing with a static system, so you're able to more easily collect the data. And notice that the differential equation involves an acceleration. That means if you're working with video analysis, where your primary data is a displacement, to get to an acceleration, you have to differentiate twice. Well, numerical differentiation, like any derivative, involves a difference over a difference. Well, noise is a difference. And every time you numerically differentiate, you magnify the noise. Sometimes by the time you get to acceleration, all you have is noise. So it's best not to work with the differential equation, in this case directly, but with an algebraic model that's derived from the differential equation that can be used for the model testing. So take a look. Let's take a look at the issue of model testing. What you see in this graph is not a best fit line. This is actually a model line, because we have the luxury here of knowing the values for the parameters, g, 4, pi, etc. And this is actual data collected from Harvard Introductory Physics Lab some years ago. And when you see the model line and you see the data, and then ask the question, how good is the fit to the model? Well, when students are presented with this, typically they will say, oh, fit's pretty good. It looks like the points are on the line or nearby. But once you zoom in, because these are error bars, we find this, large discrepancies between the data and model. Those error bars represent 1 sigma, or standard error. And notice that we're several sigma or more away from the model line. In other words, this is a huge discrepancy. We would have to actually reject the model based upon these results. So the best fit to the data could be a bad fit to the model. And in fact, the best fit may not be a good fit. Well, the curve fitting methods that are commonly employed, well, they go back to 19th century. I mean, nothing wrong with that. Calculus centuries old. But you'll notice something missing from these methods. Nowhere in the equation for the least squares is there mention of measurement uncertainties. And that gives rise to an outlier problem, right? Because if we treat every data point as equally certain, then one data point could skew the results. We'll see how chi-squared solves that and many other problems. Now, central to chi-square parameter estimation and model testing is the central limit theorem, which, just as a kind of just a brief summary of it, the distribution of the sum of random variables tends towards a Gaussian with some assumptions. Typically, we'll prove this to students using a Python simulation, where we sum together from various distributions, even uniform distributions, and we end up with a normal distribution. And then we actually use some real-time data collection from an ultrasonic motion sensor just aimed at the ceiling. And as we acquire the data, it turns out to be normal distribution. We're further assured that not only based on the simulation and the physical experimentation, that we're going to generally be dealing with Gaussians in physics experiments, because, and anytime you use chi-square analysis, because notice we're using means because of multiple measurements, multiple trials. Means are sums. So they're just the distribution of means is going to tend towards a Gaussian. And we need to use mean values because of the multiple trials to obtain the measurement uncertainties. And I'll just mention as an aside, but relevant here, is that sigma actually in physics denotes standard error, not standard deviation, because standard error can be reduced by increasing the number of trials, unlike standard deviation, which cannot. So now, with that as backdrop, let's see how chi-square actually develops into a method. So we've already established that we're on safe ground if we assume a Gaussian. We rewrite a Gaussian function in terms of a data and a model. That's here at the bottom. So y naught, or y initial rather, one value of the data point, that is the data. And then y model is whatever model we're using. That could be ax for one parameter linear model. But notice that it includes in the denominator the uncertainty, which is what sets this method apart from ordinary least squares. So now we apply a method that's called maximum likelihood, and it's as follows. A person doing model testing is likely to ask the question, well, given the data, how probable is the model? And the fact is, there's really no good answer to that question, how probable is the model? But if we invert the question, turning it on its head, and then paraphrasing JFK's inaugural speech, ask not, given the data, how probable is the model? Ask instead, given the model, how probable is the data? That's a question we can answer. So we draw a Gaussian around each data point, which is a mean, and we ask, given the model, what's the probability of generating all the data? Well, that's a tall order. So what do you do when you have a problem that's too tough to answer? Well, I know nowadays it might be to ask ChatGPT, but at one time the answer would be look for a simpler and similar problem. So a similar and simpler problem is, what's the probability of generating one data point given the model? Well, that's going to be given by the Gaussian. So we start with that, and then the probability of obtaining all the data is just obtained from the normal laws of probability. If you have a succession of events, you multiply the probability of each event. So with the base of the exponential, we get in the exponent the sum of these yi's minus y model I squared over 2 sigma I squared. Now we introduce chi-square, we define it as the sum of that numerator and denominator in order to simplify the expression. And notice now, using chi-squared, we get this beautifully simple result that the probability given the model of generating the data will be proportional to e to the minus chi-squared over 2. Well, that means to get the maximum probability, we need the minimum value of chi-squared. So what does that look like? Well, chi-squared is a parabola, it's a quadratic, but the actual probability function is a Gaussian. So when chi-squared is minimum, that corresponds to the peak of the probability. There's a switcheroo in terminology. When you express probability as a function of parameters, that's called the likelihood. So that means we now have a method of parameter estimation, find chi-square min, and it will correspond to the maximum probability. And then we read off what that slope is. And I'll just mention to you that this also gives us the estimates for the uncertainty of the best fit parameter, because if we go to chi-square min plus 1, notice that corresponds to 1 sigma on either side let me go back to that, 1 sigma on either side of the best fit parameter. That will give us now the range for the best fit parameters uncertainty. So this is the best fit parameter at the minimum, and then we go out chi-square min plus 1 on either side. That gives us the best fit parameter uncertainty values. Now that we have the best fit parameters and their uncertainty, how about a good fit criterion? Well, a reasonable fit to the data, we'd expect most of the data points to be within about a sigma of the best fit line. Now, if you're thinking, well, it should be right on the best fit line, no, that would not be a reasonable fit. That would be a highly unlikely occurrence that all the data would be on the line. We expect measurement uncertainties. So a reasonable fit would be to be within 1 sigma. And look what happens. When you substitute in the difference between the data and the model as 1 sigma, sigma squared over sigma squared is 1. Summing from 1 to n gives us n. Now we have a good fit criterion. A good fit will be if chi-square min is approximately n, the number of data points. We can go a little further by realizing that since the standard deviation, which is root mean squared deviation of chi-squared is the square root of 2n, we can get a good fit range of n plus or minus the square root of 2n. That's a good fit range. So let's take a step back for a moment and just summarize all that this methodology is providing us. It gives us the best fit parameters. We just look for chi-square min. And notice that it solves the outlier problem because it weights every value inversely by the square of its uncertainty. So if an outlier is a very uncertain value, it's going to contribute very little. And that isn't available if you do just ordinary least squares or what one would do in ordinary curve fitting. But not only does it give us the best fit parameters, it gives us also a determination of a good fit if chi-square min is of the order of n. And as I mentioned before, we can actually extract the uncertainties on the best fit parameters by looking at plus or minus 1 sigma on either side. But wait, there's more, just like those commercials that are selling some product and they say, wait, there's more. Well, there's a couple more things that chi-square can do. You can use chi-square min to gauge improvements because once you improve your experiment, you now expect that chi-square min should get closer to n. We should get a better fit. Moreover, we have another independent method of testing our model because if we do have the luxury of knowing what the reference or true parameters are, we can see how far the best fit parameters are from those reference parameters. And if greater than 2 sigma, we would reject the model. So 2 model testing methods, as well as being able to determine best fit parameters, their uncertainties, and gauging improvement, which is the scientific method, constantly iterating and testing, changing your model. So what simplifications did we introduce to make this method easy to use? There's a few. One is we use closed form minimization, the vertices of a parabola and paraboloids, which high school students know how to find the minimum of a parabola. This replaces complicated nonlinear numerical minimization algorithms. It makes the Python code short, readable. We also restrict to 1 and 2 parameter linear models. Now, that may seem at first to be restrictive, but notice many nonlinear models can be recast in that form. The simple pendulum, that was a nonlinear model, but we recast it by equating, for example, t squared with x and L with y. The assumption that's being made here that simplifies is that we assume all measurement uncertainties are in the dependent, not the independent variable. That's a good assumption for a lot of physics experiments because if you vary, say, the masses are known pretty well, and then you're just looking at the uncertainties in the independent variable. So those are the simplifications. And let's take a look at some examples, how it's used in practice. So this is from an experiment that was done in MIT's 801 mechanics class last term. A uniform circular motion experiment. It involves a rotating shaft, a spring, a ball, and as the shaft rotates, the ball starts to move further away, the radius increases. On the right is a derivation starting with Newton's second law, and we end up with a differential equation, a theta dot squared, and we cast it in the form of a two-parameter linear model, y equals ax plus b. And because it involves theta dot instead of theta double dot, there's less problems if one needed to do numerical differentiation. Here's the results, and this is what chi-square analysis actually gives you. So on the left is the data points, the best fit line, and the error bars, and also a summary of the results. So we have 5 data points, but chi-square min was 11.79. It was higher than the good fit range, not by a lot, but a little. That means we'd have to reject the model. Chi-square analysis is an exceedingly sensitive technique. It doesn't mean that we throw away the model. It means often we revisit the experiment to try to improve it. And that's one of the nice things, that it deals with both experiment and model. Notice the error bars tell us a lot. Notice that since x is 1 over r, on the left side is actually the greatest radii, and that's where the biggest error bar was, because when the velocity, angular velocity was great, there was a lot of wobbling taking place. So you can see that the error bars, the analysis, it tells us a lot about the actual data itself. On the right side is a contour plot for the two parameters, where this represents the 68 and 95% contours for the best fit parameters. The best fit parameters right at the crosshair. That's the best value of A, the best value of B. A second example, falling chain. This was from an experiment, the Harvard physics lab. This is an interesting experiment. Falling chains, you can get the result where the acceleration is greater than little g. This is not free fall. A person is holding a chain that's been folded, and when then they drop the end of the chain, there's the bullwhip effect where the acceleration can actually exceed little g. It's easiest to understand that in terms of energy, where this system largely conserves energy. There's not a lot of frictional loss, and as a result, you've got the case where the kinetic and the potential energy, as shown here in the model, the kinetic energy is only from this second side, the other side stationary. The potential energy is from both, and by applying the work kinetic energy theorem, the change of kinetic is negative the change of potential applied to this particular problem, that would be the application of the work kinetic energy theorem, we end up with a differential equation for x dot squared. But in terms of the underlying idea behind this, then we've got a potential energy that's being converted into kinetic, and the mass keeps decreasing as there's less and less of the chain that's moving. So with the same energy but less mass, the actual velocity and the acceleration diverge. In fact, I understand that maybe one of the first times that humans had broke the sound barrier was actually with the crack of a whip. That is, that can actually result in a velocity exceeding the speed of sound. So notice that we end up with this nice result, which would be challenging to symbolically integrate, but we are only needing to numerically integrate it from 0 to 1, where we've got x reaching the total length. And this is an elliptical integral. It can be solved with easily just Wolfram alpha to get the numerical result. A nice simple result. TF is the final time. That's the time for the chain to reach the bottom. And look how simple the model becomes. The algebraic model derived from the differential equation, the final time is 0.38 times the square root of L. It's a one parameter linear model. And how was the data collected? Well, 5 different videos were taken, and the video analysis was done with Tracker. And if there's 3 students per group, each one collects the data from the video. So that gives you some variability in order to do the chi-square analysis. And this is some results actually from a high school student using the video analysis provided, and reject the model because notice chi-square min is 38. That's above the good fit match. But even though it tells us to reject the model, it just reminds us chi-square is very sensitive. So what it does is it tells us to go back, revisit the experiment before tossing out the model, see if that can be improved. And all that the rejection is telling us is that given the model, the data wasn't generated to within 1 sigma. So a few takeaways. A model testing method related to parameter estimation exists. You don't have to use one method for parameter estimation, another method to test a model. One method can cover both. To really test a model, you need measurement uncertainties. I mean, sometimes you may not want to go to extremes to test a model, and some of the other methods they're useful and they may be sufficient. But if you're serious about testing a model, you need measurement uncertainties. That means multiple trials. The data points will be mean values and the error bar is standard error. And if possible, just a takeaway, to extract an algebraic model from a differential equation model. It simplifies the data collection and it avoids numerical differentiation, which will increase noise. And thank you.